Hi, in this session we'll be talking about the problem of joint lives, and through it we'll be introducing a useful tool called indicator variables. The problem of joint lives is the following. We have two M people who are paired into M couples. Each couple consists of a first partner and a second partner, and what we're told is that at some later point in time, each individual, each person, has a probability P of being still alive. And if it helps, you can think of this later point in time as something more concrete, say 50 years down the road. And we're also told that whether any person is alive is independent of whether any other person is alive. So this person being alive has no probabilistic effect on whether or not, or the probability that this other, his or her partner is still alive. All right, so let's define a couple of random variables, as the problem says. Let's let A be the number of people still alive 50 years down the road. And this is random because each person has some probability of being still alive. And let S be the number of couples still alive. And a couple being still alive is defined as being both partners in that same couple are still alive. So if at least one person is no longer alive in that couple, then we consider that that couple is no longer alive. All right, so with these definitions, what the problem asks us to calculate is this conditional expectation. What is the expectation of S conditioned on A being some little a? Now, what does this actually mean in words? What it says is that suppose I tell you that there are exactly little a people who are still alive 50 years from now. Then, given that, what is the expected number of couples who are still alive? And of course, this is going to be a function of what little a is, so it depends on exactly how many people are still alive. Now, you might think and say, well, the answer is pretty obvious. It's probably a over 2, right? If there's little a people left, then each couple has 2 people. Then if there's a people left, then there must be a over 2 couples left. But in fact, that's actually not right, because in order for a couple to be alive, both people have to be still alive in that same couple. And that may not be the case for all the A people who are still alive. They may not just happen to fall into couples. So in fact, the answer should be less than A over 2. And exactly what it is less obvious. And we'll have to do some calculations in order to do this. And it seems actually that it might be difficult to do because S is not it's not some clear random variable that we've dealt with so far. Now, the trick in this problem is to try to think about, can we split S up into its component parts? All right, so what is S? S is the number of couples who are still alive. Let's just split this up into each individual couple. And if we can somehow calculate whether or not any given couple is still alive, maybe if we can then aggregate that up, we can figure out what this conditional expectation is. And that really is the idea behind indicator variables. So what exactly is an indicator variable? Well, it's actually really just a Bernoulli random variable. It's either 0 or 1. And we call it an indicator variable just because, in this case, it's supposed to indicate whether or not a certain event has occurred. So let's define a couple of indicator variables. Let's let xi be 1 if the first partner in couple I is still alive 50 years from now. Now, notice that we've actually specified that this is the first partner. So within any couple, let's let one of them be the first partner and the second one be the second partner. So this is just a Bernoulli random variable, but we call it indicator variable because it's supposed to indicate that whether or not the first partner in couple I is still alive and is 0 otherwise. And similarly, let's define yi to be 1 if the second partner in couple I is still alive and 0 otherwise. All right, so why do we bother with doing this? Well, now we can define another random variable, zi, to be the product of xi times yi. Now, what is this? This actually is also an indicator variable. It's 1 if couple I is alive, and it's 0 otherwise. Now, why is this? Well, this is the case because zi is 1 if and only if xi is 1 and yi is 1. Right? If at least one of these two indicator variables is 0, then their product is going to be 0. So zi is 1 if and only if the first partner in couple I is alive and the second partner in couple I is alive, which is exactly the event that that couple is still alive. And so what we've done now is we've kind of broken up things into individual couples, and we've calculated out or defined a random variable that dictates whether or not that couple is still alive. And now what we do is we aggregate up, because it turns out that S now is just the sum of all these zi's. All right, because S is the account of the number of couples who are alive. Zi tells you whether any given couple is still alive. It's 1 if that couple is alive and 0 otherwise. So if you just add up all the zi's for I from 1 to m, remember there's m couples total, then this will give you exactly S. And of course, this is just xi times yi. All right. Now we've rewritten S as this summation, and now we can plug this back into the original conditional expectation that we want to calculate. So the conditional expectation of S, given that A is just the expectation of the sum of xi times yi. And now we can use linearity of expectations, right? Because this is just a sum of m terms. Expectation of a sum is just the sum of expectations, and even in the conditional world, that is still true. And so this turns out to be just a sum from I equals 1 to m of the conditional expectation of each of these xi times yi's. And remember, we still need to keep the conditioning on A equals A. All right, and now we can further simplify this, because we can observe that it doesn't actually really matter which I we're talking about, because of the kind of the symmetry, and all the people have the same probability of being still alive, and they're all independent, and so because of that, each of these expectations, this expectation is for a couple I, and then you have another couple, but all of these are going to be the same no matter what I is. And so what we actually have is just m copies of the same conditional expectation. And so let's actually just be specific and just focus on, say, we can focus on any of them. Let's just focus on the first couple. OK, so now the quantity that we want to find is this. Now what's left to do is we just need to figure out what this conditional expectation is. So let's do that. What is the conditional expectation of x1, y1, given that A is A? Well, remember what an expectation is. An expectation is really just a weighted sum. It's just you take the value of the random variable, and you weight it by the probability that that random variable takes on that value. Well, we know that x1 times y1 is just z1, which is a Bernoulli random variable, so it can only take on 2 values, either 1 or 0. And the 0 case doesn't actually factor into the expectation, because the 0 just cancels everything out, the probability out. And so it's really just equal to the probability that x1, y1 equals 1, given that A is A. OK. Now, what is this equal to? Well, x1 times y1 can only equal 1 if x1 equals 1 and y1 equals 1. And now we can use we can separate this out some more and focus on, let's say, this is the multiplication rule, and say, well, first let's focus on this. And now we'll then focus on y. So first we'll say, what's the probability that x1 equals 1? And remember, we still need to keep the conditioning on A. And then once we have x1 equals 1, then we add that to the conditioning, and then we calculate what's the probability that y1 equals 1. So this is really the same rule, except in the conditional universe, right, where a equals a. All right. So now all we have to do is figure out what these two things are. So the first one is, what is the probability that x1 equals 1 given that a equals a? What does that mean in words? That means that conditional on that there are exactly little a people who are still alive. What's the probability that the first partner in the first couple is still alive? Okay. Well, because of the symmetry and all that, every single if we know that there are a people left, then any set of a people out of the original 2m is equally likely to be the one, the a who are still alive. So now, how many ways can we choose that? Well, what we have is we have 2m people, and we need to choose a of them to be the ones who are still alive. Right, so that's the total number of ways we can pick the a people who are still alive out of the original 2m people. Now, we want the first partner in the first couple to be still alive. So his place is already fixed. He needs to be one of the a people who are left, which leaves a minus 1 people left. And those a minus 1 people had to be filled, who are still alive, had to be filled by 2m minus 1 people. Right? Because there are, besides this first partner in the first couple, there are now 2m minus 1 people left. And those are the people from which we need to choose the a minus 1 people who are also still alive. So there's 2m minus 1, choose a minus 1. And if you actually calculate this out, you will get that turns out that this is actually just a over 2m. So another way to think about this, if the counting argument didn't quite make sense, is that each person has, there are basically a slots left. These are the a lucky people who are still alive, and there are a slots left to be filled. And each person, because each person has the same probability p of being still alive, they have an equal chance of being selected for one of these a lucky slots. And so each person, so consider like the first slot of people who are still alive, the a people who are still alive. Every single person out of the original 2m is vying for that spot. And so the first partner in the first couple has 1 over 2m chance of being selected for that first slot. But he also has the same probability of being selected for the second slot and all the way through the 8th slot. So essentially he has a chances to be selected to be one of the people who are still alive. And so that's why you get the probability of a over 2m. Now let's think about the second one. Now we're conditioning on there being a people who are still alive, and we know also that one of those a people is the first partner in the first couple. Now, given that, what's the probability that the second partner in the first couple is still alive? Well, if you think about it, this probability is going to be lower than this one because we know now also that one of the a slots has already been taken by the first partner in the first couple. So the second partner kind of has less chance of being selected because one of the slots has already been taken. So it turns out that now, through a similar argument, you get that it's going to be 2m minus 1 over a minus 1. And if you calculate this, you will also get something similar. And the only difference here you notice is that the fact that this person, the first partner in the first couple, is known to be alive removes one of the slots available. All right. And so we get that this is this conditional expectation. But remember, we also have a factor of m that we need to add in. And so the final answer that we get is going to be a over 2 times a minus 1 over 2m minus 1. So that is our final answer. So I get one more word about this. You can also think of it as the same thing, because now we know that one of the A slots has been taken, so there's only there's only A minus 1 slots to be filled, and there's 2m minus 1 people vying for those slots, because we know that the first partner in the first couple has been fixed to be still alive. And so you get a similar argument, you get this expression. Now, let's just make sure that this actually makes sense. Well, we know that A is no more than 2m, right? Because there were 2m people to begin with, so the number of people who are still alive can be no more than 2m. And so because of that, you see that this thing here is going to be no greater than 1, which means that this conditional expectation, the answer that we're looking for is going to be no more than a over 2. Right? And so this is just a check, the sanity check, to make sure that our answer is actually correct. And that makes sense because if you start out with, if you have a people, there's no way that you can have more than a over 2 couples. And you notice that for a less than 2m, this expression is actually going to be less than a over 2, because this part is going to be less than 1. And this just verifies our original intuition that because not every person who is left alive will just happen to fall into the original couples, original partners, then the number of couples who are still alive will actually be less than a over 2. And only when a is exactly equal to 2m, so if a is exactly equal to 2m, then this is going to be equal to 1, and this is going to be equal to m. So in that case, if all the original people are still alive, then we'll have exactly all the original m couples who are still alive. But otherwise, it's going to be less than a over 2. So this answer, at least on the surface, seems to be something that's reasonable. Okay, so in this problem, we started out with something that seems fairly complicated, and we broke it down into constituent parts. So we take in one random variable, and we've broken down into all these indicator variables, each one representing an individual couple. And through that, the use of indicator variables and linearity expectations, we were able to calculate the final answer.